Okay, I think we can start. Hope we are audible. And maybe I introduce this is Martin Dunsche. He's from Ruhr University Bochum in Germany and is currently visiting. He's from the chair of statistics and his research field is differential privacy, but we already found other areas where we can work together in. And he will now give an introduction to differential privacy, which I think is an important topic, which is not represented very well at TI, but maybe you find it useful as well. So thank you, Martin. Stage is yours.
Thanks a lot for the warm introduction. And besides broad introduction, I would just talk briefly about myself and especially the organization I'm coming from, which you already see is CASA. So CASA is an excellence cluster in Bochum, and it actually represents IT security in general quite well, as it is like well funded by the German Research Foundation. And Bochum in general, not only with CASA, is an excellent place to do IT security. And actually in this picture, just for you to know, here is Robert. So this is where we got to know each other from. It's CASA actually. And I think I'm also on the picture somewhere in the middle. But this is a picture from 2021. So obviously Robert has now joined the TII already. And yeah, I'm a PhD student at the chair of statistics, as Robert already said. But I'm also doing other stuff besides differential privacy, but my primary focus will be differential privacy. And in this talk, I will give you guys a brief introduction to differential privacy. And afterwards, I will talk a paper that just got accepted at S&P 2024. And yeah, with that, just a few more things. So at the moment, I'm located at Bochum, at the Ruhr University, and there are still other things you can explore with correlated to IT security. For example, the Max Planck Institute is also in Bochum, and there are plenty of exceptional researchers doing IT security. So somehow similar to the CRC here in Abu Dhabi. All right. So what I'm going to talk about first, as I already said, I will give you a short introduction. So this should be accessible for everyone, even without no prior knowledge about privacy, no prior knowledge about statistics. So, and afterwards, I will talk about a paper with the title Law Bounds for Rainy Differential Privacy in the Black Box Setting, which might seem more involved, but don't worry, I will make it accessible for everyone. And let's start with the introduction. So the first thing I like to talk about is, why do we actually need differential privacy? What is the reason why researchers invented this topic? Essentially, best practice, and people still do this, when they work with data, they essentially just remove unique identifiers, like the name or the age. And what researchers have found out is that this removing is, first of all, it's still applied, for example, in pharmaceutical companies and stuff like this. For example, I did an internship at Novartis, and the current practice is that they remove unique identifiers, but still work with the true data. But researchers have found through linkage attacks that these kind of privatizations are actually not sufficient. So there are plenty of works. So for example, the most prominent one, probably the work by Narayanan et al. In 2008, where they were de-anonymizing the Netflix database set. But there are also other ones. For example, the About one in 2018 was actually looking at census data. So they were talking about the census that appeared in 2020 in the US. And this was, for example, also a prominent example of an application of differential privacy. So this was the first time that in census data, where they do aggregate statistics, actually applied differential privacy. So what do these linkage attacks basically do? The idea is, if you remove these unique identifiers, it doesn't mean that the data essentially is private, because if an individual is such a unique person that, for example, has a special medical condition or something like this, you will still be able to infer that this person was actually the person that we wanted to protect the privacy. So what differential privacy now tries to do, it wants to give you a theoretical framework that practically eliminates all possible linkage attacks. And the conceptual idea is that they want to guarantee users something that we call plausible deniability. And what plausible deniability in that sense means, we will figure this one out later. But before going into the definition, I would like to give you a bit more of an intuitive understanding of what differential privacy can mean. And some of you might know this. This is a cartoon, where's Wally? And the idea of the cartoon is that there's plenty of individuals, and we are all wanting to find this one individual that I call here Wally. And I've done the job for you. Wally is over here. But the general idea is now, and this is more of a metaphoric understanding of differential privacy, is we want to identify individuals. They are somehow hiding among other individuals. And what differential privacy now wants to do is, it wants to somehow disturb the statistic. Imagine now that this picture is actually the statistic, and it will get more difficult for you to infer where Wally actually is. So in this picture, I think with the prior knowledge, we still know that this is most likely Wally, right? But if you disturb the statistic even more, I think in the example C now, we can already see that it's not too easy to get to actually infer properly that this is really Wally. So, and from the transition from B to C, there's actually also a really interesting understanding of differential privacy. So if we want to protect the privacy of people, we could also just remove all the data, use no data at all, and this would be perfectly fine from a privacy perspective. But in reality, we want to learn something about the population. So there is a natural trade-off in privacy and statistical accuracy. And this is depicted here as well, right? So we can still infer a lot of things about this picture, but it somehow protects the information of individuals. So the individual level, there is privacy somehow, but we can still see that there's a beach, we can still see that there's a sea, there are people around the sea, there are ships, these kind of things we can still infer while we protect the privacy of individuals, right? And an extreme example now would be, what if we want full privacy, so there's no possibility of assessing someone on this picture, is over here. Just remove basically any information, right? This is not a desirable case. So A and D are both non-desirable cases. The cases B and C, these are what privacy people are somehow trying to negotiate what is the best practice to get statistical accuracy against privacy. So what statisticians have now done until now is what people call differential privacy. And this is the classical definition of differential privacy. Actually, first, it appeared without the delta. So think of delta being 0, but let's go through it. So it might seem difficult, but at first glance, but it is actually quite accessible. So we have two privacy parameters, one being the epsilon, and the second one the delta. The primary privacy parameter is here the epsilon. That plays the important role. And we now have something that we call a randomized algorithm, M, that takes as an input a database X. And we call this algorithm epsilon delta differentially private if we have a data set and we consider all possible other data sets X prime that differ in one component. So we replace one individual, the distribution of M of X or M of X prime, they are kind of close to each other. And what do I mean with close? So close here, for example, consider delta equal to 0 and assume that epsilon is small. Then essentially this inequality, because it holds for all X and X prime and for all possible outputs, means that the probabilities are close to each other. And when the probabilities that M of X takes some value or M of X prime takes some value are similar, then there is something that we call plausible deniability, because the individual input does not matter on the output. So the output, M of X being A, is as likely if the individual that is replaced was part of the data set or not, right? So in X, it is part of the data set, and X prime, it is not. So this is what researchers in differential privacy call plausible deniability. All right. So you might, from the definition over here, you might not be able to really say what is something like a randomized algorithm. And today I've brought, I think, the most simple one, which is called the Laplace algorithm. What it essentially does is, if you have some aggregate statistic you are interested in, let's say f of x, let's say it's the mean, right? The mean of data is like the most simple aggregate statistic you can look at. Then the Laplace algorithm basically takes it as an input and adds some random noise on it, right? L here stands for a random variable that is Laplace distributed. You don't really need to know what it is. Essentially, it's similar to a normal distribution. It is symmetric around 0, and with a specific noise calibration. And the noise calibration now is somehow calibrated by 2 parameters, one being the epsilon. Epsilon now calibrates the privacy we want. And the delta F here, this might also seem somewhat complicated, but essentially what it captures is, if I replace one person from the data set, how can my statistic change? So if you're now considering the mean, it can change essentially to 1 over n or constant over n, right? So it essentially just captures how much my statistic can deviate. All right, and this algorithm is provably epsilon differential private. So this is one possible way of constructing a differentially private algorithm. So with this, we can already somehow fulfill the definition I was giving you on the prior slide. To make it a bit more practical, let's just go through a simple example. So assume now that we have data x1 to xn, and also assume the data is distributed somehow. For those who have practiced differential privacy already, they will now notice that this actually is not bounded, so it would not really work out. But just for demonstration, just assume that this works out. And we are considering the mean I was already talking about, and we want to disturb the mean, so we want to construct a differentially private output. So, as in just depicted now. Here, what I've done, I've simulated f of x 10,000 times. So I've computed 10,000 mean statistics. The distribution looks the following way. So as we expected, if I generate normal data, the distribution will look exactly that way. It's actually independent of the normal distribution. It also would look the same if the distribution is differently. The main idea is now what happens if we add this Laplacian noise. And the quintessence is the following. So what I've depicted here now are 3 different scale noises. So essentially I've set epsilon to 0.1, then I set it to 0.01, and then I set it to 0.001. And you might think, okay, this illustration seems like nothing really happens, right? But there's actually an essence here. What really changes if we change the scale, the privacy scale, is now that we add basically more variance. And this is how you could understand differential privacy. If you have a statistic and you want to make it differentially private, you're essentially getting more noise, right? You're putting noise on the data. And this can be seen here because you might have not seen it here, but the scales are different. So the first picture where epsilon is 0.1, the x scale is actually from -5 to 5. And for epsilon 0.001, it's actually from -500 to 500. And if we zoom in and use the same x scale, you will see essentially that at the beginning, it's kind of close to the original distribution of the data. When I apply epsilon 0.01, you can already see that there's quite some noise now appearing apparently. And in the third picture, you can actually see that this is almost close to a uniform distribution. So what would a uniform distribution mean? Essentially, it's independent of the input of the x. So the data does not really influence the output nowadays. So this would, in that sense, mean that it's statistically useless to assume that kind of scale with this amount of data that we observed. And this heavily depends on the sample size, by the way. So if I would increase the sample size, this noise scale might actually work again. So yeah, with this intuition, so maybe just to summarize it a bit. So what differential privacy does, you have some kind of statistic, you want to be able to give individuals of the statistic plausible deniability. So you're noising the statistic in a sense that people who would try to infer some individuals from it cannot do this properly anymore, right? So this is what we have now learned. This is what differential privacy does. And now coming to the paper that I wrote with my co-authors, Tim Kutter and Askin, who is actually also from CASA. we considered the following framework. If you have some kind of algorithm M that is supposed to be differentially private, then we want to assess the privacy actually. So we asked ourselves the question, how private is this algorithm? So we wanted to actually estimate the privacy parameter epsilon. And we considered two scenarios. First being the scenario where you have no access to the algorithm. So essentially, you know that a third party guarantees you this algorithm is epsilon differentially private, and you want to verify it now. This is one scenario you had in mind. Another scenario, and that is also, I think, reasonable, is if you're unable to prove. So usually if somebody does differential privacy, he will prove that it is epsilon whatever differentially private. But sometimes if these algorithms are too complicated, or this will definitely play a role in this privacy implication, you sometimes only show bounds. So you show this is at least that much private and up to that. So I will just mention a few later this talk where this might be useful. And then estimating this epsilon might actually be interesting, because then you can see if your bounds are tight or not. So this would also be an application that we had in mind somehow. All right, so let's give you a motivation. So we were not the first that thought about estimating this epsilon. And there were previous works, one being from Bichse et al., and the other one actually being from my co-authors that I mentioned prior. And they only considered the case where we looked at pure differential privacy. And in pure differential privacy, the scope is not enough, at least from our perspective, because in pure differential privacy, you cannot assess the privacy of multiple algorithms. The most famous one definitely being the Gaussian mechanism, where you do exactly the same as in the Laplace algorithm. You just replace the Laplacian noise with Gaussian noise. But there are also some other algorithms. For example, the subsampling algorithm, which is a privacy amplification. So essentially, you do your private stuff, and you are just adding in a subsampling algorithm, and this makes it more private. The same holds for the shuffling algorithm. You're shuffling the data, and this also is a privacy amplification. And assessing the privacy of these algorithms can actually be difficult. So sometimes they only provide bounds. And yeah, and another really prominent algorithm would be, for example, the noisy gradient descent. And this would also not be able to be quantified under pure DP, essentially because it's using the Gaussian mechanism. All right, so with that, okay, so we thought we should extend the previous work, and we will consider a different privacy definition to the pure differential privacy one. All right, so the relaxation we are looking at now is called Reni differential privacy, and it is based on something that mathematicians usually call the Reni divergence. And the essence here is now that prior to this, in the pure differential privacy, we are looking at these probabilities, right? If you remember, we are looking at probability of the mechanism being in some output. Now we're replacing these probabilities by looking at the actual densities, and they can be discrete or continuous. So when they're discrete, they are actually probabilities. When they're continuous, they are densities. And the Reni divergence is then defined by this. The quintessence here is now not to really understand what this exactly means, but essentially it is a measure on how close these densities are or not. And with this divergence, we can consider the following definition. So assume again, you have some algorithm M that is supposed to be somehow private. Then we have, again, two privacy parameters, one being lambda, the other one being epsilon. And now we call M lambda epsilon Reni differentially private if for all adjacent, in this case means again neighboring data sets, so we replace one individual, the Reni divergence is actually bounded above by epsilon. And what kind of Reni divergence are we looking at? We are essentially looking at M of x, so the density of M of x compared to the density of M of x prime. So we are looking at, again, a mechanism evaluated on x and a mechanism evaluated on a different data set that is differing only in one component. So if this is bounded above by epsilon, then we call this mechanism epsilon differentially private. And to give you some intuition why this is actually a reasonable definition, You have to trust me on this one. If you have the definition, you can prove the following. So for any x and x prime and any output A, you can essentially look at the following inequality. And let me just explain what is going on here. So you have the m of x, and these are the probabilities of m of x, and you have the probabilities of m of x prime and m of x prime here. And what is different now are the following exponents. So essentially, the relaxation that really happens are these exponents by lambda. And if we want to get back to the previous definition, we essentially just say let lambda go to infinity. Then we are exactly at the previous definition of pure differential privacy. The true relaxation also so happens only if we consider a fixed lambda. Let's say lambda 2 or 5. If we say, for example, lambda is equal to 2, the following is supposed to hold. So the distributions are, the probabilities in that sense here, are close to each other, but not as close as in the previous definition where we had pure differential privacy. So here we have a square here, and a root here. So they are still somehow close to each other, but not as close. And with this definition, we can actually infer about the privacy of the Gaussian mechanism, the subsampling algorithm, the shuffling algorithm. So this is a feasible definition for our purposes. All right. As I said, just let me recall, what did we want to do? We wanted to assess the privacy of these algorithms, right? In a black box setting. So we might not have access to the algorithm, we don't know what it outputs, and so on. So the principal idea is now we want to estimate this epsilon. And let me just maybe go back to the definition. So we want to estimate this epsilon via this divergence. So essentially what we want to look at is the following. We want to find these pairs, x and x prime, where we maximize this divergence, right? So we have, when you're thinking about privacy, the privacy parameter is captured mostly when you are looking at databases where you have extreme differences. So you're looking at where x prime and x, the individual that is replaced, is actually the unicorn, right? The 1 in a million person. Then the privacy parameter epsilon is actually fully used. And this is already the heuristic that somehow explains how we could estimate this epsilon of lambda. And to just illustrate it, imagine we just choose random x and x prime that are differing in one component, but we have not chosen the ones that are furthest away. Then we might get something, an estimator, I call it LB because it's a lower bound, that might not be too close to epsilon of lambda. And if we repeat this procedure, we can get eventually close to epsilon of lambda. But obviously, if there is some heuristic how we could choose the x and x prime to make this more efficient, it would be quite desirable property. And to make clear what kind of x and x primes we would use, let's look at an example. So if we are at the unit cube of d dimensions, then being furthest away from in data sets means now that if, for example, we have x equivalent to the 1 and the other entry is equal to 0, then the furthest away would exactly be x prime when we have x prime being only the 0 vector, right? Because these are the furthest away in exactly this space. And the heuristic, and I will show it to you in later simulation evaluations where we try to find and estimate the epsilon, you will see that this heuristic works quite well, actually. All right. So as I said, we wanted to estimate the following divergence. And when we want to estimate this, what are we doing? We are essentially estimating the unknown distributions P and Q. And how do we estimate things in statistics? Obviously, we need to generate samples which we use to estimate these distributions. So the essence here is, as I said, we want to estimate the following. So we use the specific x and x prime and essentially estimate P and Q through kernel density estimation. And here I want to emphasize that we use a non-parametric approach because we are in a black box setting. If we would not be in a black box setting, using a non-parametric approach is probably not optimal. So if you, for example, know my algorithm is Gaussian distributed, you would never just use the non-parametric approach. You would just use and estimate the parameters of the normal distributions, right? Because that would be that would improve the performance significantly, or could improve the performance significantly. All right, so what statisticians usually do if they want to estimate a function of something, can we not just use the plugin estimator? So we take the estimator of P, we take the estimator of Q, plug them in, and then we get an estimator for the whole divergence. And in fact, this is not really feasible here. And the reason is the nature, the structure of the divergence. So essentially, what you're doing is you are dividing by one density. And these density, especially think of the normal distribution. You all know the normal distribution, the density, like these, the curve, probably all of you have seen it. They are not supported on a compact subset. So they are approaching zero in the tails. And if we now estimate it the following way, we would divide by small values. And dividing by small values that are close to zero is definitely not a good thing to do. Not a good practice, especially in statistics. You will notice that this is not robust then, and it will actually explode and make the whole statistic inference be useless actually. All right. So with this, we said, okay, if we cannot just use the plugin estimator, we have to somehow construct an estimator for our distribution Q that is somehow bounded away from zero. And this is, I would say, part of the novelty of this paper is we essentially constructed an estimator that is bounded away from zero and did the statistical inference, because the inference actually got way more involved. So the theory we have developed got more complicated due to this technicality. And what we have did, so here I display the normal distribution, and you already see it's quite close to zero. By the way, it's not zero, so don't get misleaded here. It's never zero, but it's close to zero. And obviously in computers, we can only work with finite precision. So this is somehow at some point zero in a computer, right? So what we do is we essentially floor our distribution. So what happens is we cut off these tails that are close to zero and set them to a value tau that is pre-specified as an input. And with that, we are bounded away from zero. So we are not, let me just go back. We are not having this problem of dividing by values that are really close to zero, right? So we get some kind of stability. However, this somewhat changes the statistics behind it, because we are not estimating the actual distribution anymore, because we are now using the following estimator, and this is somehow introducing any kind of bias. Because flooring, we cut off the information essentially, and flooring then obviously introduces a bias. And this bias is now a bias below, so we will underestimate our true divergence usually. And if we now would use a larger tau here, so let's say the red line, this would also actually mean that the bias that we introduce is also larger, because we are further away from the true distribution. However, the problem is also, you have seen it, maybe let me go back once more to the divergence. If we are dividing, but if we let now tau be small, because we want to have an almost unbiased estimator, right? So, then we would divide by small values. And we would even have an exponent lambda. If lambda knows, let's say, also taking some higher values, then we would divide by a small value that would make the value extremely large. And then we would use the exponent of an extremely large value. This is not really good, because then the variance basically explodes. So there is a natural conflict that appears more often in statistics, which we call usually a bias variance trade-off. So we have to somehow balance it. And the parameters that are important here are then, or the parameter here that is important is tau. There's actually another parameter which I've not talked about here, which appears in the kernel density estimation, but you don't really need to worry about it because it's a more of technical nature. All right. So with that, so now I've explained how we constructed our estimator. And the logic behind now is essentially that we want to estimate the d lambda, right? This is what I told you. And the reasoning is now, if we now take a sample size large enough, this is what a sample size is called the n, then we have the following. First of all, it means that essentially the data approximate the two distributions good enough. And if we now let tau to be small enough, the flawed version should also be close. So Q tau should be close to Q. So essentially, the estimator we have built, we've set up, is somehow close to the true diversions, right? Making this formal is really complicated, actually. So the proof is like, I think 5-6 pages or something to get this one line, essentially. But yeah, this is what the paper delivered. And to put this kind of equation in a more easy way to access. So essentially what we have built an estimator that is somehow close to the true divergence. And this divergence actually is now our epsilon, right? The true epsilon, the privacy parameter of the mechanism. All right, so let's get to some evaluations where we tested our method if it actually works in practice. So for simplicity, we have considered this simple example, database X. Again, the unit cube of dimension 10 at the moment. And again, as I said, what this comes back to the example that I gave you prior to this. Being first away in that space for neighboring datasets means that it has exactly a 1 metric 1. So the distance between the vector 1, 0, 0, 0 to 0, 0, 0, 0 is exactly 1, right? These are the data sets we have chosen. And we have chosen some parameters. Now, there's no need to worry about these, but essentially what the following plots will show you is the following quotient. Our estimator, I depicted here as, I denoted it as L hat divided by the true privacy parameter. So L hat is supposed to be close to epsilon. This is what we are depicting. And if we are now looking at our first algorithm, let me just quickly explain what it does. So randomized response essentially is an algorithm that gives back a 0 or a 1 with a certain probability. And then if the probabilities are chosen appropriately, then it fulfills some differential privacy condition. And what we have added here is the shuffled algorithm. So if you are also shuffling it, it actually fulfills a better privacy, right? The privacy is increased if you're shuffling the data. And what you see here now is actually a problem that appeared through the black box setting. Obviously, the parameters here, they are all fixed. And this is important because we cannot just adapt the parameters because we don't know the algorithm, right? So there you can see that if we are increasing the lambda, the estimator will actually be worse. So if the y-axis is the quotient I was talking about, so our estimator divided by the true privacy parameter, you see that the estimator is kind of still close, right? Because we are still above 0.9, but it degenerates somehow. It gets worse for increasing lambda. And the problem here is just that the bias dominates, right? I've told you about the bias introduced by the thresholding, tau. So what you can essentially do here, if you have any more knowledge about the algorithm, you can choose better tau. So previously, we had a tau that was 5 times 10 to minus 5. And now we have just increased it by 1 magnitude. And then you can see actually that our algorithm has a really tight bound. So essentially our estimator is almost perfect, right? This is like heaven for statistics, the estimator. And yeah, this is one example. Another example would be the Gaussian mechanism. What you can see here, again, it seems to be quite stable actually. So we always surpass the 95% number, which is quite satisfying actually. And yeah, obviously sometimes we are always also overestimating the true privacy parameter. This is just due to the statistical nature. So we allowed a false positive rate of 5%. So we expect to have at most 5% surpassing our actual true privacy parameter. This is what we allowed. And yeah, to come to an end, another algorithm would be the noisy gradient descent. And again, here you see the same problem appearing we had previously. Essentially now here, it's not the bias that is causing the problem. We see that there's quite some variance coming from the exponent actually here. And again, these problems can be resolved by optimizing the parameters, but this is the nature. We assume that we are in a black box setting, so we did not optimize our parameters, and then these kind of things happen. Still, this is still a good estimator, so don't get me wrong. This is actually working quite well. All right, so feel free to ask any questions, and if you want to reach out to me and talk about differential privacy, you can just come by at the office or just contact me through mail. All right. Yeah, and here are some references actually.
All right. Looking at the chat. I don't see any questions.
Yeah, sure. Go ahead.
So here you're estimating a lower bound for the epsilon and the differential privacy.
Well, so I think we are estimating actually, so we are not estimating a lower bound. We are estimating the epsilon, but the only possibility to estimate the epsilon is via a lower bound. So we can just from the constructional point of view, we can only do a lower bound. Because the reason actually is, first of all, one reason is the following, that we are thresholding it. This is one reason, because essentially the denominator is always smaller, always larger than the true denominator. So we are always, the estimator will always be a bit smaller. And another nature is here that we are actually, if we want to estimate the epsilon, we would have to estimate the supremum. So to estimate the supremum, we would have to go through all x and x prime. So we obviously cannot do this. So we choose heuristic, where we say we just use the furthest away because they are essentially representing the true epsilon quite well.
Also, if you go back to the previous slide, the relation between running entropy and differential privacy.
Mm-hmm.
Differential privacy is an upper bound of running entropy, right?
Yeah, that's true. Essentially, if you are going back here, so Ringy differential privacy is a true relaxation of pure differential privacy. If you set lambda, let lambda go to infinity, then on the left side, lambda divided by lambda minus 1 would go to 1. And here, lambda minus 1 divided by lambda would also go to 1. So essentially, if lambda goes to infinity, this is exactly the definition of pure differential privacy. So it's a true relaxation. And has nice properties, actually. So there are plenty of things to consider there as well.
Is there also, is there a relation known between the different lambdas? For example,
yeah,
running entropy with lambda 1 is always
exactly. So essentially, the Rayleigh divergence is monotone in lambda. So if you increase the lambda, the epsilon will also increase.
For any input, for any distribution.
Yes. Yeah, it's monotone. Yeah.
So there, I mean, in your estimates, you stopped at lambda equals 7.
Yes, this is definitely needed also. So we actually pointed that out in the paper. Because you're taking the power here, if you would take values of lambda that are extremely high, this would be statistically hard to analyze actually. So there is some natural conflict between taking higher lambdas and getting a good estimator. So good point. Definitely lambda should somehow be bounded. You can probably still do, so we did it actually. We did also do simulations with 10, but we already noticed that it will somehow not work as well anymore. So we said, okay, get a reasonable, because also if you put lambda equal to 7, you will see that here, this is already quite close to the true differential privacy definition. So lambda equal to 7 would be something like 1.15, and here would be 0.85, something like this, right? Roughly like this. So it's quite close already, right? So it's reasonable to only consider lambda equal to 7. It's not ridiculous. Yeah. but 10 would also work. It's not like we did not exclude it because it was not working anymore. It's just the performance will degrade with higher lambda. Yeah, good point.
Another question? Can I ask another one?
Yeah, sure.
So if you go back to the mechanisms, you had a list of 4.
Yeah, sure. Where was it? Or maybe prior. Yeah, here.
Yeah, I'm familiar with Gaussian, but I don't know what the other ones are.
So the subsampling essentially is you subsample your data, then there's a probability that an individual is not chosen. So this somehow improves the privacy.
So this you can show as differential private.
No, it's not differentially private, it's an amplification. So you are doing some privacy usually, like let's say Gaussian mechanism, but then you include the subsampling, then it is, you get a better epsilon essentially. The same holds for the shuffling, you're basically shuffling the data. And the noisy gradient descent is just, so you have heard probably of gradient descent. It's some optimization algorithm. Essentially, you want to find a maximum or a minimum. These kind of gradient algorithms, so ascent or descent, whatever you are looking at. And noisy already induces it. It's a differentially private version of a gradient descent.
What is it? So the other 2 are amplification methods. This one is
noisy gradient descent. It's a mechanism itself, and I think it's one of the widely used ones actually, really important. So if you train models and you want to do it differentially private, you usually use these kind of. So especially in machine learning, they use this everywhere. And the field of differential privacy machine learning is like, yeah, crazy. So it's this is also like one of the main reasons why we did this paper, because we saw like, okay, these kind of mechanisms, they need to be, you need to be able to assess the privacy of them. This is why I included it actually, because I think it's so important.
Thank you everyone for joining online, and see you in the office. Thanks.